All right, welcome back. We have 2 more long talks to go. The next one will be by Irene Lo, who will talk about simple and approximately optimal contracts for payments for ecosystem services. Please.
Great. Well, thank you so much, all of you, for being here and for the organizers putting together this really fantastic workshop. I'm very excited to be here to talk today about simple and approximately optimal contracts for payment for ecosystem services. And this talk is going to have a slightly different flavor to a lot of the talks in this workshop, because here we're really trying to drill in one particular application and look at how some fairly simple contract design and contract theory can be useful in this one application. And so I'm still learning both in the space of where a contract useful from simple contracts rather useful from an applied perspective, and what does that mean for our algorithmic and computational questions. So happy to learn along with all of you. And in particular, the work I'm going to show you today, a lot of this I learned from my inimitable student, Wanyi, who kind of drove the field research interviews and the model building in today's work. Okay. So the application we're going to look at today is something called payment for ecosystem services. And the idea here is we're going to pay owners of natural assets to conserve those assets. And by we, you should think of, for example, an NGO or a local government or a national government and some kind of government program that's paying these people. Such PES programs have been growing in popularity all over the world, including in the US, China, Mexico. And one particular prominent example from 2017 was in Uganda, where a randomized controlled trial by Jayachandran et al. Showed that using these kind of payment for ecosystem services to pay smallholder farmers to not deforest reduced, in that instance, deforestation by 50%. Okay, but by and large, there have been rather mixed empirical findings on the efficacy of PES in all kinds of different applications. Today, we're going to focus on forest conservation. And in that particular application area, there is quite a large empirical work, and it finds anywhere from 50% reduction, this very groundbreaking paper, to basically no impact at all. So the question we're going to try to address today is, let's try to take a contract design, a theoretical perspective to this question of PES contracts. And we're going to ask, can we explain theoretically under what conditions we would find PES contracts effective? Specifically, once you come in with a contract theory approach, you see right away that all of these programs that are set up basically have the same structure, what we call their conditional contracts. Essentially, the forest owner is paid if and only if they conserve all of their forest. Okay? And so if you cut down even a small number of trees, then you're not just paid anything at all. And so this is obviously a very particular form of contract. There's like one action you can take, which is conserve everything. And if you don't take that action, then you get nothing. And if you do take that action, you get paid a predetermined amount. And so the question is, when is this specific kind of contract effective for PES? And then can we improve on this by designing other contracts that are still simple to understand, which we can talk about with our collaborators at, say, the Natural Capital Project or the Nature Conservancy, and they won't say, okay, that's too complicated, but which nonetheless still have some performance guarantees theoretically. So today, what I'm going to do is just set up our very, very basic principal agent model. I'll talk about our theoretical results on the performance of a few different kinds of simple contracts, and then I'll show you a numerical study that we ran using United States land use data. First, a quick slide on related literature. There are a lot of different streams of work that this paper kind of is trying to draw on. The first, as I mentioned before, is that there's quite a large literature in the environmental sciences on payment for ecosystem services. And those are generally more empirical studies or looking kind of at broader things about how the program is set up. And so as far as we can tell, there's just been this one paper looking at payment for ecosystem services more from this contract design perspective, and their model is the one that we're going to be using today. we're here at a workshop on contract design, so you don't need me to tell you about all the wonderful and really interesting literature in this space, but we're going to draw primarily on, there's all the old literature, of course, on the structure of optimal contracts. Our setting is very simple, and so you can just directly apply all of that. But also, we're going to be thinking about robust contracts, which contracts can perform well even if some of the parameters in the underlying regime are changing. And then finally, I think, just giving a little bit of a plug for this general area of natural capital market design or natural capital contract design, applying some of the tools that we here at EC are very familiar with to this space of environmental applications. Okay. So with that, let me jump into the model. This is going to be a very simple principal agent model that we'll be taking directly from this Mason and Plantinga paper in 2013. This was primarily some theory and simulation paper. First, we have an agent, and the agent owns some amount of forest area. And this amount of forest area is going to be observable. And you can think that, in the past 5-ish years, satellite imaging technology has really gotten so good that just using that, the principal, like the local government, can use that to monitor the amount of forest area that is owned and not deforested by the agent. What's going to be private information to the agent is what we're going to call their baseline conservation level. You can think of this as a lot of these agents who own the forest land are smallholder farmers. And these smallholder farmers have all kinds of stochastic costs that come up. For example, they have some medical expense, they have some educational expense, and so that particular year they have a particular need for money, which they could get some money quickly by cutting down some trees. And so that's going to be their private information, which we're not going to know. But what the principal does know is the distribution from which this type, theta, is drawn. And how does the type of the agent affect their utility? In particular, I mentioned this cost. We're going to model this quadratic conservation cost, where here's a picture of it. Let's say I conserve my baseline amount, theta. Okay, then my effective cost for doing so is 0. Okay, but if I conserve any more than this is kind of like the marginal utility to me of like cutting down an extra tree and being able to farm more on that land or sell the timber. Okay, and so I have these increasing marginal costs. And that's going to lead to, in this particular case, we're using the quadratic cost function. I'll briefly mention what happens in general convex functions. And so then the agent's utility is going to be whatever payment that the principal gives them for taking the action, net the cost of taking that action. Okay, very, very simple model. Now moving to the principal. The principal has some environmental value, K dollars per unit area forest that is conserved. Now this is actually not without loss in this particular application area, because here we're saying that the principal has this like linear value for the amount of forest that's conserved. And so this might be reasonable if you're thinking, for example, of carbon sequestration, right? Like one tree here, one tree there. It doesn't matter if the trees are next to each other. But let's say you're interested more in something like biodiversity. Right? Then you really do care about complementarities between are the pieces of land next to each other, what is the existing biospecies that are on in that land. And so this is an assumption that we'll need today and is going to be with loss, but is still applicable if we were, for example, paying people to make sure that we can sequester carbon. Okay, and so one way you can think about this K is something like what's the social cost of carbon and how much of that is being reduced per unit area of tree that's conserved. What the principal is going to do is they're going to select a contract, and the contract will tell the agent if you pay some amount, if you conserve some amount of forest A, I'm going to pay you some amount that depends on your conservation amount. And we're just going to have one agent and one principal today. And so the principal is trying to solve the following standard optimization problem. They're trying to maximize their point with my hand. They're trying to maximize, this is the value of the area that's conserved, net the payment that they have to give the agent. And then we have our standard incentive compatibility, individual rationality, limited liability constraints. And on top of that, there's an additional little wrinkle. And so let me just jump into what that wrinkle is. The optimal contract, we're going to take a direct revelation approach where depending on, we basically give this menu of options so that the agent of type theta will choose the corresponding theta. Well, they'll take action A theta and be paid amount P theta. And so then we're going to solve this classical contract program with the additional boundary constraint, which is that the agent cannot conserve more than they already have. Okay, but this is still very standard, right? You can still basically solve it using all the standard ways. Just to spell it again, my objective, this is my total environmental value of conserved land, net payment to the agent. My incentive compatibility constraint says that the agent prefers to take the action for their type rather than for a different type and be paid that amount. Individual rationality says that the agent gets positive utility from doing this, and we're not going to be able to tax the agent. Okay, so we're paying the agent, that we're not asking the agents to pay us. Okay. And so if we take this standard contract theory approach, we're going to get an optimal contract that looks something like this. I'm not going to spend too much time explaining the shape of the optimal contract. The thing to take away from here is on the left here, I have my payment regime as a function of theta. On the right here, I have the conservation quantity. And the thing to take away is that this optimal contract is something that's really complex to implement in these smallholder farmer settings. Right? Like we go and we were actually talking to some folks at the Nature Conservancy who were telling us, oh, actually it was a group that was trying to, certify a contract approach that was taken at a project at the Nature Conservancy. We talked to both groups, and essentially what was novel about this particular application is that they offered a menu of contracts. You're not just taking one action, you can either plant this amount of grass, or like a medium amount of grass, or a high level of grass, and there are different payments for this, and they were already like, oh my gosh, this is like so complicated. Who's going to be able to like use this and track how it's performing? So when I'm saying simple, I mean like really, really simple. Okay? And so something like this, where I don't just have a menu of 3 options, I have a menu of an infinite number of options, and it's this sort of, to us, simple function, but to them a complex function of what they do, is just not going to be feasible in practice. Okay. And so that kind of motivates our main question for today, which is, are there simple contracts, so simple that these folks would be happy to implement them, but which can get close to the performance of the optimal contract? Today, we're going to explore just 3 kinds of simple contracts. Actually, I'm going to talk about just 2 results from 2 of them. The first are these conditional contracts that are currently being used in practice. So recall, this is basically one action, you conserve everything, no deforestation, and one payment corresponding to that action. An obvious extension of this kind of contract, which has been brought up a couple of times today, is what's a linear contract, right? So I'm going to pay you, if you conserve 100%, I'll pay you 100% of what I promised. If you conserve 50%, I'll pay you 50% of what I promised. And then there's a third set of contracts that kind of interpolate between those, saying that I'm going to pay you linearly in your conservation amount if that conservation amount exceeds some threshold. Right? So if you conserve at least 80%, anywhere from 80 to 100%, I'll pay you proportionally to how much you conserved. And our measure for all of these contracts will be the percentage of the payoff from the optimal contract, which I showed you on the previous slide, that this particular contract can achieve. Okay. So let's look at how these contracts perform. First, let's look at conditional contracts. Recall these are the ones that are currently being used in practice. You pay, the way they phrase it is actually, you pay an amount that's proportional to the amount of forest area that's conserved, but only if you conserve everything. And the reason they frame it this way is because today we're looking at just one agent, but really they're writing like one set of rules for many agents that are all participating in the same program. Okay. And so how do these contracts perform? Well, actually, the performance of these contracts is going to be split into 3 regimes, and these regimes are going to be governed by these, this K over H. What is K over H? I'm sure you've already forgotten my model by now, but the K over here is the principal's per unit value for per area of land that's conserved. And this H was hiding a little bit. This you can think of as the agent's marginal cost of conserving beyond the baseline amount. Okay? It was basically the multiplier I had in front of my convex, my quadratic costs. And so what K over H is giving me is this ratio of the relative value to the principal of the land compared to the agent's value for the land. Okay, another way you can think about it is the way that in our numerical study we look at these relative values is K is kind of the environmental value of the land, which is what the principal cares about. And then the H is kind of the agricultural value of the land, which is what the agent cares about. Okay, so let's look at these three regimes. First, when the environmental value is very large, then the best conditional contract is actually the same as the optimal contract, and all of these contracts just pay the agent a lot, right? Because my environmental value for the land is very large, much larger than the agent's value for the land, I'm going to pay them enough to induce them to conserve everything. Okay. When K over H is very small, my optimal contract is going to be, first, my best conditional contract is going to be no contract. Okay? The agents are not going to opt in. I'm not going to be willing to pay them enough for them to really take that full conservation action. And this is, in general, different to the optimal contract, which I'll show in the next slide. Okay. Next, when we're in this intermediate regime, the best conditional contract can actually perform arbitrarily poorly. What's going to happen is again, the best, actually I misspoke a little bit, and what I'm going to show you on the next slide is for this intermediate case, where the optimal contract is going to want to induce some intermediate amount of conservation, but the best conditional contract is not going to pay enough to induce any action. Okay, and so here's an example illustrating that. We have just one agent type, super simple. There's no information asymmetry. Their baseline is they're going to not conserve anything. Okay. The best conditional contract is you either pay the agent to conserve fully, or you don't pay them and they don't conserve anything. The best optimal contract is going to be something intermediate. Okay, don't worry too much about the specific numbers, but what you can kind of see is that they're going to conserve an intermediate amount if this K over H is in this intermediate regime, and I'm going to pay them some non-zero amount, and I get some non-zero objective. And what happens is that if K over H is kind of in this small to intermediate regime, my conditional contract is not going to pay the agent at all. The agent is not going to take any action, and so I get 0% of the payoff that I could have in an optimal contract. So let's move now to our next set of simple contracts. These are linear contracts, and recall I told you this is basically how they're already phrasing the contracts, which is you're going to receive an amount that's proportional to what you conserved, or this many dollars per hectare conserved. But now we're just not going to have the condition that you need to conserve all of your land. And so here's what we can show. We can show is that for any value of K, that's the principal's value for the land, any value of H, which is that parameter governing the agent's value for the land, as well as the distribution F over the agent types, there is a distribution-free linear contract that always achieves at least half the payoff of the optimal contract. Okay, and so an obvious corollary is that the best linear contract is always achieving half of our desired, at least half of our desired objective. Okay, and this is in contrast in the conditional contracts where you can get 0%. Okay, and just to repeat sort of what's surprising here, this linear contract does not depend on my values of k or h, or actually depends on the value of k. Okay, the only thing it depends on is the value of k. It doesn't depend on h, it doesn't depend on f. Okay? What I'm doing is I'm paying my per unit price is going to be k over 2, which is half of my environmental value per unit land. And so a summary of the results so far, we basically have these 3 regimes for the relative environmental of the value of the land. If it's low, then the conditional and linear contracts both kind of perform like the baseline. You don't really pay the agent anything. That's optimal anyway, because you don't really have high value for the land. If it's high, then the conditional contract is actually going to be close to optimal. And in general, the linear contract, I didn't show you this today, but you can show is going to perform not as well as the conditional contract. And then what's interesting is in this intermediate regime where the conditional contract can perform arbitrarily poorly, whereas the linear contract always gives at least half of the optimal payoff. And in fact, it's this distribution-free linear contract that gives you at least half the optimal payoff. And so kind of the takeaway here, if we were to go to some practitioners and say, well, what does this mean for your contracts? We kind of have this simple kind of, if you have really high environmental value, you can keep using the contracts you are using. But if you have lower environmental value, then you might consider getting rid of that stringent conditionality requirement and paying proportional to the amount conserved. And so we have some extensions. I told you about also these conditional linear contracts, which kind of interpolate between being conditional and being fully linear. What we can show is that, well, obviously, the best conditional linear contract always does better than the best linear contract. But in fact, we can also choose these instantiations for the thresholds that are independent of my distribution f, which are going to do better, and in simulations actually are going to do well for both intermediate and high k over h. And then we can also extend this to general convex cost functions. What's going to happen is my half, that was really coming from the quadratic. And so now the half is going to change depending on bounds that I can place on kind of the second derivative of my function. Okay, great. But what I really want to show you in my remaining 5 minutes is, what can we do? How do we go from this theory and saying like low k, intermediate k, high k? What does that look like in a real life application? So the study I'm going to show you today is using US land use data, and this was the main contribution of this Mason and Plantinga paper where I got the model from, is they collected the data to be able to estimate their model. And so lots of thanks to them for this wonderful data set. And what that means is because we have the same data, they're estimating exactly the same parameters as we are using in our model. And so we're going to take this baseline conservation distribution directly from their estimates, as well as conservation cost. Okay, and so just to give you one example, what they did was they kind of looked at land use data from across the United States, and then kind of state by state characterized places in that state where the agricultural value of the land was very high versus medium versus low, and kind of estimated these Fs and Hs in each of those areas. And so here I'm showing you for Montana, this is low deforestation risk. This generally means that the outside value of the land, for example, for agricultural purposes, is not very high. Okay, so what I'm plotting here is the best conditional contract in blue, the best linear contract in red, the baseline of not paying the agent to do anything in green, and I'm highlighting this little sliver here where my linear contract is going to do better than my conditional contract. And so just going back to our theoretical takeaways, one thing that we observe is indeed the conditional contract is going to be optimal if I have high environmental value. I'm just paying the agent to conserve everything. And then there's this intermediate regime where linear contracts improve on conditional contracts. Okay, so this is what happens if we have low deforestation risk. This is essentially if my value for H is not very big. So now let's look at an example, also in Montana, of high deforestation risk. Okay, and what we see is that this intermediate regime, where my linear contract, the red line, improves on the conditional contract, the blue line is now much larger. Okay, so let's take this one step further. What I originally asked you was, well, where do our parameters fall here? Where's K? Right? What is my environmental value for the land? So let's say we say my environmental value for the land corresponds to the social cost of carbon, which admittedly is kind of high for what most of these programs are going to pay, but let's go with that for now. That's going to correspond to a value of just the way we set up our model, or the way that they set up their model, a value of K equals 100. Okay? And so you can see that if we're in the low deforestation risk regime in Montana, then the conditional and linear contracts are kind of close. But if we're in the high deforestation risk regime, then there's suddenly a gap between these two types of contracts. And we do expect linear contracts to be able to improve on the conditional contracts. Okay. Another question you might have, well, this is all in the US, but most of the countries I showed you that have these PES programs are running them in developing world settings. Okay, so what do things look like there? The honest answer is it's really hard to tell because we don't have this kind of detailed data in those settings that we do in this particular US setting. But what we can do is we can kind of do a back of the envelope calculation based on the agricultural value of land per hectare in Brazil, or whichever country we are interested in here. And so here we're doing it for Brazil. And what we find is that the agricultural value of land is about half that of what we were using in Montana. And so what that would do is it would move my line for K from, I'm thinking about K versus H. So that means K is going to be doubled if H is halved. And so now I'm expecting to do even better in terms of switching to a linear contract compared to a conditional contract. Okay, so that's essentially all I wanted to talk about today. And from our paper, we have this observation that there are all these contracts that are being used in practice, and they have these implicit structures that the people designing these programs have never thought about. And in the case of PES, this implicit structure meant the contract can perform arbitrarily poorly. What's driving this is that the conditionality condition as a requirement is too stringent. And so there's very low take-up in these programs. And when we say these to people, the program sort of managers, they say, oh yeah, actually this makes a lot of sense. That's what they're seeing on the ground. And this is particularly true when the relative value for environmental value of the land from the principal is low or intermediate. What we showed is that a distribution-free linear contract can guarantee half the optimal payoff. And then we also ran this numerical study using US land use data from which we can kind of corroborate these results, see that the gaps are most pronounced when deforestation risk is high, and also probably in developing countries. Just a few closing thoughts in line with the themes of this workshop. First, for this paper in particular, there's a lot of things that we've left unexplored from the theoretical side of things, which you could definitely go off and write a bunch of theory papers. Just thinking about complementarity of forest area, thinking about, I motivated these costs by saying they're often stochastic and unknown, and they're kind of evolving over time. And so Nicole with Wanyi and Brendan, they've looked at a model which does incorporate some of those stochastic costs, but I think there's still a lot more to do in that model. From an empirical perspective, just being able to get a better sense empirically of what do these costs look like could give us a much better sense of which regimes are in, which types of contracts are likely to perform better. And then one direction which we've really come across a lot in talking in these developing world settings is this idea of group contracts. The contracts that the people are used to doing they're not used to this individual view of like me as a forest owner conserving my forest. They're thinking more at like the village level, like what should we as a village commit to, and then how do our like internal leadership decisions kind of govern what happens if someone kind of reneges on their promises. And so I think there's a really big opportunity for thinking about mathematical approaches to this group contracting. A couple other thoughts. There's a lot of potential extensions mathematically to be studied, which I just kind of listed out for us. But I think that the main takeaway is that there's this growing line of literature on simple contracts, approximately optimal contracts, robust contracts, distribution-free or prior-free contracts. And I think there are a lot of use cases out there for that type of contract, and this is just one of them. So really invite you all to join me in looking for more. Thank you.
Thanks a lot, Irene. Very nice talk. Do you have questions?
Testing again? Perfect. Thank you for the talk. This was a really interesting topic. So one of the things that I noticed pretty early on was that we were really consistently referring to the ratio between K and H, as opposed to just K or just H when doing these models. And I can imagine how a policymaker could estimate K pretty easily to just pick a value. But for H, it seems like it's harder for a policymaker to figure out what it is, and that if the cost function isn't simply a quadratic function, that also seems to be harder to estimate as well. How robust are these results to both H changing around or that cost function changing around? There was a slide in it, but we skipped past it really fast, and I was interested in it.
Yeah, great. The question was, how robust are the results to particularly the value of H? Because H is something that's often difficult to estimate in practice. Okay. So just going back to the theoretical results. So in the particular case where my cost function is quadratic, this contract that I'm choosing, which gets me half the optimal payoff, actually does not depend on H. That's great. It depends only on K, which is the parameter that's easy to estimate. Okay, it doesn't depend on H, which is kind of the scaling for the agent's value, and it doesn't depend on F, which is my knowledge of the distribution of the agent's type. Okay, so that's really great, but that's only if my cost function is quadratic. Okay, so once I go to it being not quadratic, and it looks something like this. Actually, again, my bound is going to be not as good. It's going to depend on the curvature of my function. But again, you can see that I have a threshold value of K star. That value of K star does not depend on H, but it does depend on my estimates for this curvature of the function. Okay. And so I think there's room to tighten basically all of these. We were going more for a proof of concept. And in the simulations, I think you do see that the value of H matters quite a lot in terms of the magnitude of the improvement, as well as what values of K give you an improvement. But I think if we look at the values of K here that we thought were reasonable, especially if you double them all, which would be more in line with sort of developing country costs, then even in this, this is small h versus big H, we're pretty solidly in the middle of that regime where the linear contract improves on the conditional contract. And this is true not just in Montana. I'm showing you just Montana, but in the paper we have it for a lot of the other regions across the US as well.
All right, thank you. So I would, maybe one quick question.
Sure, yeah, for a minute. I'm curious, in practice, does the contract designer have enough scale such that the design of the contract could affect the value of H? Right? Because if you make everyone conserve rainforests, then maybe the value of H will skyrocket because if everyone's using these contracts.
Yeah, what a very interesting question. Yeah, we have the effects on the market value of agricultural land if we have enough scale. My sense is that currently these programs do not have enough scale, and there's also a lot of other external things outside of this one period contract model to worry about, well, what do they just conserve while you're monitoring them and then you leave and then they cut down all the trees? So there's a lot of other things outside of this beautiful model to worry about, but that's a really interesting one I hadn't thought about before.
That would be a great problem to have.
Yeah.
Yeah, that's true. Yeah, thank you very much for the nice talk. Thanks.